I have, so I'm going to seal this so that no heat exchange with the atmosphere. And then I have here oxygen, and then let's say helium. So now let's say the pressure of the oxygen is, let's say, 4 atmospheres. And the volume is 1 meter cubed. And let's say the temperature is 400 Kelvin. And then here, the pressure is 2 atmospheres. The volume is 2 meters cubed. And the temperature is 250 Kelvin. So you could have just 2 random gases. And now let's puncture a hole in this barrier and then allow them to mix, the oxygen and the helium, right? Or you could just take the barrier out completely. Take the barrier out, allow them to mix, and at the end you have something like this. The O2 is kind of everywhere, and then the helium is everywhere. So this is kind of a gas mixing problem, where you have 2 random gases at different temperatures, different pressures, and different volumes, right? And then you mix them, and we want to know at the end, what's the pressure of this gas? What's the volume of that gas? What's the temperature of that gas? Of this gas? How do we solve something like this? So strictly speaking, this is not one of the usual type of thermodynamic problems, but it does fall under there. We're not doing any work on it. It's not exchanging heat with the environment, but it's just they're mixing together. So then what's going to happen? The heat will flow as the gas is going this way. Heat will flow from the hotter moving molecules, right? This is moving at 400 Kelvin. And then heat will flow towards the colder molecules. So these are moving slower. So the velocity distribution of the helium should start increasing, right? So if the helium's velocity distribution looks like this, it should start looking like this. They should start moving faster and faster. And then, of course, the opposite will happen to the oxygen. The oxygen is already moving fast, right? And so the oxygen will start slowing down. At the end, they should reach the same temperature, right? They should be equilibrium.
Yes.
Yeah. So probably I'm expecting the final temperature to be between the two. It can't be anything else. It has to be between 400 and 200 Kelvin. Now, which one is it closer to? Is it closer to the 400 Kelvin or is it closer to the 250? That depends on how many moles of helium I have, how many moles of oxygen I have. So you see, which one it's closer to depends on how many moles of helium, and then depends on which one is diatomic. See, diatomic is harder to lose its temperature. Remember how we said the specific heat of a diatomic is higher than a monatomic. It takes more heat to change its temperature. So that alone tells you the final temperature is probably going to be closer to 400 because diatomic is harder to lose its temperature. But we still need to know which one is more moles we have. That also matters. So let's calculate the number of moles of oxygen. We do P1 V1 over RT1. Right, so P1 is 4 atmospheres. 1 meter cubed over 8.314 times 400, right? And then change atmosphere to, well, you know what? I could leave it as atmosphere and then change this to liters and then use the other version of R rather than multiply this by 1 atmosphere is 101.3 kilopascals, you know. So I'm just feeling a little lazy today. So I'll just leave it as atmosphere. Then I'll just say 1 meter cubed is 1,000 liters. Right? Then I'll just use the other version of the R. 0.08, what was it? 0.080. This one, 0.08205 liter atmosphere per mole Kelvin, 0.08205. 0.08205. Okay, so then I should be able to calculate what the number of moles. Number of moles of oxygen, 121.8769. The number of moles of helium is going to be its pressure 2 times 2 times 1,000 divided by 0.08205 divided by its temperature, which is 250. Oh, I've got more moles of helium. Well, now I can't predict where the temperature is going to be because I've got more moles of helium, but helium is a monatomic gas and its temperature is easier to change. Oxygen is harder to change, but I've got less moles of oxygen. So I'm not sure if the temperature is going to be closer to this guy's or that guy's, right? Okay, so then what's the next step?
Professor, I have a question.
Yeah.
Those numbers that we got, is it reasonable as well because there is a change in the volume?
Yeah. Which values did I got?
Because I mean for volume, you put.
Oh yeah, well because this one said the initial volume of this is bigger, so I put 2 here.
Right. So the fact that it's bigger, right? Helium is bigger.
Huh?
You mean the volume? So the volume for helium is bigger, right?
For this one here. Say that again. I'm not sure what I know what your question is.
So what I'm trying to get to is the volume for helium is bigger than the volume for oxygen.
The volume, yeah, is helium is bigger, yeah, than the volume. So maybe see this is constrained like this.
Right.
So originally you're told that this is the barrier is closer to this guy. So you're given the conditions that this gas is in and then this gas is in.
Right.
And then they mix.
So we're saying that the number of helium molecules is reasonable just by looking at the volume?
Yeah, just by looking at those conditions, yeah, the number of molecules of helium are reasonable, yeah.
Okay,
So
I was
In
just
other
wondering
words,
if
in order for helium to be that cold and still be 2 atmospheres
you need a lot.
and occupy that much volume, you need to have that many moles.
Yeah. Okay, yeah, that makes sense.
Yeah.
So we could make more. We could make a deduction more based on the volume of that. We'll have more molecules of one or the other, not so much the diatomic or monatomic. That'd be more for the
Oh yeah.
energy.
Right now, I didn't use diatomic
Molecules.
monatomic.
Yeah.
But-
Yeah,
really
nothing
for the-
like. Yeah, I didn't use any because moles doesn't care diatomic monatomic.
Gotcha.
Yeah.
But the temperature also says a lot too, right?
Oh
If it's
yeah. of
colder, you
course.
have a lot
Yeah,
more.
yeah. So this problem would have been the same if I had worded it this way. If I said you have a bag of oxygen and another bag of helium, and then I said this is an empty container. Then you take those bags and you put them in here and then you puncture them, and then you close the container, and then you puncture those bags. But I give you the initial conditions of the two bags and their original pressure and their original temperature, right? So then it's still the same. You put them in there and you puncture them and you let them mix. Okay, now here's where the monatomic diatomic concept is going to come. As they exchange each other, so let's say here's the barrier. As this guy goes over here and as that guy goes over here, they're going to exchange heat with each other, but not the surrounding, right? So then you have Q into the oxygen is going to be delta E of oxygen plus the work done by oxygen. Let's see, oxygen was what? It was 400 Kelvin. And then the helium was 250 Kelvin. So actually oxygen is going to be giving heat to the helium. So now what's going to happen? Remember that as the oxygen is diffusing, it doesn't do any work. This is a adiabatic free expansion. So this is zero. But it is cooling because this is slightly different than the previous adiabatic free expansion we did. When this guy expanded, it wasn't cooling at all because it was just expanding into free space, you see? So the work was zero, the delta E was zero, and the Q was also zero. Here, you're expanding and then you're exchanging heat with a colder gas. But as you're expanding, you're doing no work. So Q out of the oxygen is going to be delta E, where it's going to be, remember, delta E is NCV delta T. Right?
So, Professor,
yeah.
Could it be just like that? Also, it's like a perfectly inelastic collision with the molecules versus the piston. Would you be able to say that, or?
You mean with this and this is perfectly elastic, and then while it's hitting the piston, it is
inelastic.
No, I don't think so. No. In the piston, you're actually doing work against it by pushing it. Here, you're doing no work. You're not pushing anything.
Okay.
Yeah.
Even though they're colliding with each other, but when they're colliding, it's just.
Yeah, but that's a random collision.
Okay.
You're not like colliding with a particle and then pushing it to one side, right? You're not like colliding and then saying, okay, I'm going to push you, expand you.
Got it. Yes. Okay.
Yeah. It's like a random diffuse collision.
Got it.
Okay, so now the Q out of the oxygen is going to be NCV. And then now here's where the CV of the oxygen is going to come in. So this is diatomic, 5 halves R. And then the T initial of the oxygen minus the T final. Right? And then we're going to do the Q into the helium is NCV delta T of helium. And then CV of the helium is 3/2 R. You see, that's where. So in other words, if the helium accepts some amount of heat from the oxygen, right, and it's accepting that heat in the form of collisions, essentially. As this guy is, it's not like heat is like some weird, some weird wavy thing that comes from oxygen. We tend to think of it as this kind of wavy thing, but in this case, the heat that it's accepting from oxygen is the bumping of the oxygen molecules as they're moving faster. It's not radiation heat. It's not infrared heat, That's kind of the weird thing in this case, is that when we say heat, it's so general that we could mean different things. In black body radiation, heat is actually infrared heat. But in this case, it's just the molecular motion. It's just faster molecular motion. Okay, so then we have Q into helium and CV, and then the delta T is T final minus 250. Then we're going to say the Q out of the oxygen must equal to the Q into the helium. Heat conservation. Q out of oxygen is Q into helium. So this is kind of like what we do in the lab that we do today. When we take a hot aluminum, we put it into water, and then we say, find the specific heat of the aluminum, right? Same kind of example, we do heat conservation. Now we're just doing that to gases. So then we say number of moles of the oxygen, and this is the number of moles of the helium. So what was the number of moles of oxygen? 121.8769. 5 R. Number of moles of helium?
195.0030.
Okay, the R cancels, the R cancels, the 2 cancels, the 2 cancels. Okay, let's put this in Wolfram. (326). So the final temperature, it's like so almost like right in the middle.
I have a question, Professor.
Yeah.
I noticed that for the heat of oxygen, you did 400 minus the final heat.
Yeah, because I want to make a positive number equal to a positive number.
Okay.
You can't have a negative number equaling a positive number, because the final temperature is going to be between 250 and 400. So it's going to be less than 400 and greater than 250, right?
Okay.
So this has to be positive and this has to be positive.
Mm-hmm. Yeah, otherwise it would cancel.
Yeah. Now, if oxygen had been carbon dioxide, it would have been 7, right? 7/2 R. So what would the temperature then be? Instead of oxygen, carbon dioxide. it makes the temperature closer to the 400, right? Yeah, 338. You see that what it happens? If instead of oxygen you had carbon dioxide, the final temperature of the mixture would be closer to that of the carbon dioxide, which is at 400 Kelvin. Because carbon dioxide would be harder to change its temperature. It's a triatomic molecule. But since it's oxygen, this is beautiful. I love this problem. Gosh, 326. Is that exactly in the middle? Because the middle of 400 and 250 is what? 75? 325. Oh, wow, it's very close to the middle. That's because we had more helium too, right?
Right. And
That
the difference in temperature. Yeah.
Yeah.
Volume.
Why does it say equals Alan Turing? That's weird.
Is that the Alan I know?
Oh, related queries. Yeah. Okay. Well, once you find the final temperature, now how do you find the final pressure and the volume of the gas? Well, volume is easy because it's just going to be the total volume of the two containers, right? So if you're given that the volume here is 1 and the volume here is 2, the total volume is 3, right? So then we can do P total, V total is nRT total. So T total we already know is 326. R is 8.314. Oh, you know what? Let's use the version, the other one, 0.08205. And then N is the sum of the number of moles of both of them. So 121.8769 plus 195.003. So this is the ideal gas law. This is the net temperature of both of the gases combined. This is the total moles. The total volume is 3. And then
Just
the total,
divide by 3.
huh?
Yeah, no, you're good.
Yeah, then you just times total pressure, and then you divide this by 3. Okay, so then we have plus 121.8769 times 0.08205 times 326.531 divided by 3. Is that atmospheres? It's moles. 0.08, 326. Isn't that too big?
Pleasure?
Yeah.
The other constant for R only works if you have it in liters.
Oh, I forgot. Yeah. We gotta convert this to 1,000. Yeah, 3,000 liters. Yeah, so divide this by another 1,000. Because I thought 2,000 atmospheres, that was way too much. Okay, it's 2.83 atmospheres. Okay, let's see if that makes sense. If this one was 2 atmospheres and this one was 4 atmospheres. Oh, okay, so the final pressure is in between the two. 2.83 atmospheres, yeah. It's closer to this guy, but it does make sense that the final pressure is between the two pressures of the two gases. Yeah, nice, huh? Good problem.
So this explains why the plot we see that the pressure goes down. but not dramatically. Because
Ye-
it is similar to that of an adiabatic free expansion, but the only thing that changes it is the fact that we have two different type of molecules.
Yeah, let's see here. This is a bit different because the process for each particular gas is not even adiabatic free expansion anymore. It's actually accepting heat. Hold on, let's see. It's accepting heat, but it's changing its temperature. But the work that it's doing is 0. But it's not isothermal either. Oh, dang it. It's like a weird, it's none of the above. So like if we were to draw the PV diagram of the helium, the helium's volume starts out at 2 and it's going to go to 3, right? So you go 2 and then it goes to 3. Helium's pressure starts out at 2, and then the volume, the pressure at the end is 2.83. So some kind of a graph like this. And there actually is heat that flows into the helium from the oxygen, but the area under this graph is not a measure of the work done by the helium. It does no work. So what kind of a graph is this? A straight line or a curve? I'm not sure. I would, let's see, as the pressure is changing, P is nRT. As the temperature is dropping, the volume is increasing and the pressure is increasing. This is for the helium. So this is dropping, this is increasing, this is increasing. Maybe it's curved like this. But it's not truly adiabatic because it's accepting heat from the oxygen. Yeah, it's some kind of a weird curve, but I can't tell what the equation of that curve is. But it probably doesn't matter because we don't need to take the area under that graph anyway, because it doesn't do any work. You know, so it really doesn't matter. All that matters is what it starts out as and what it ends at. And the oxygen's volume starts out at 4 and at a pressure of, no, sorry, at, what was the oxygen's volume? Oh, no. Oxygen's volume starts out at 1 and its pressure is 4. Right? And then it drops, the temperature drops like this. And I can't tell the equation of that because it's not truly adiabatic. I mean, it's adiabatic because it doesn't exchange heat with the environment, but they give heat to each other. So So it looks, the oxygen's PV graph looks something like that. Starts at 4, ends at 2.83, and then the helium's goes up like that. Some kind of graph, but I can't really tell if it's straight line or not.